On November 15th, NASA finally released new images of ThreeI Atlas, and the situation is becoming more unsettling. ThreeI Atlast, once classified as a comet, has now become the epicenter of one of the most disturbing debates in modern astronomy. What began as ordinary observations quickly unraveled into a sequence of inexplicable anomalies, post-perihelion expansion, in size, continuous emission of molecular oxygen, without corresponding chemical reactions, symmetrical internal structures and thermally stable hotspots pulsing with unnatural precision. High-resolution radar from Mars Express combined with spectral data from JWST pierced its outer shell, revealing perpendicular corridors, vertical towers and a heat profile far too orderly for any known comet. Some scientists have quietly raised the possibility of an artificial construct. Others insist it's merely an extreme natural event. But what if both are wrong? We now begin the journey into NASA's latest visuals of ThreeI Atlast captured just after its velocity changes near solar perihelion. At 03:47 UTC, the European Space Agency's Mars Express orbiter registered an anomalous radar echo from a point in deep interstellar space. The signal originating from ThreeI Atlast's projected path was weak, nearly drowned in cosmic background scatter, but it was unmistakably structured. Initial waveform patterns suggested sharp phase returns, inconsistent with dust or gas trails typically associated with natural comets. The scientific community was stirred, though most agencies withheld formal interpretation pending further imaging. Mars Express's radar package, while designed for subsurface Martian scans, was oriented to catch peripheral solar objects near opposition. Atlast appeared as a translucent blur on the edge of the sensor field, a shimmer lacking any discernible nucleus or tail. Unlike Oumuamua, which passed through the solar system in 2017 with a well-documented trajectory, Atlast offered a fragmentary radar profile. There was no reliable albedo mapping, no rotational light curve, and no definitive estimate of axial tilt. The anomaly wasn't just in the signal's faintness, it lay in its refusal to behave. Atlast reflected radar in clustered pulses rather than a coherent bounce-back signature. Geometric modelling teams attempted to reconstruct the object's shape using Fourier transforms, but the results were erratic. No known natural form, spherical, cylindrical or irregular, could explain the intermittent angular echoes. There were moments of sharp edge returns followed by absences followed again by reflected beams in opposing vectors. This led to a secondary hypothesis. Perhaps ThreeI Atlast did not possess a single rigid body but multiple moving surfaces. If so, the configuration would have to shift dynamically akin to panels or membranes adjusting orientation in response to radiation pressure. But such structures imply intention. Intentionality suggests design, and design in this context demands reconsideration of the very category to which Atlast belonged. Yet no one would commit to such a claim, at least not officially. Instead, the scientific community labelled the radar signature as non-conclusive, urging caution. But beneath that caution, the unease spread quietly. The first image of ThreeI Atlast was not a revelation, it was an absence, and from that absence the questions multiplied. It was not Mars Express that broke the silence, it was James Webb. As ThreeI Atlast crossed into its most observable window, the James Webb Space Telescope executed a deep scan coordination protocol in conjunction with Earth-based arrays. For the first time in the history of interstellar object observation, a resolution of 12 meters per pixel was achieved, revealing not a blurred streak of cometary drift, but the sharply defined contours of a solid irregular body. What emerged from the composite imaging data was not merely a rock. Atlas displayed panel-like geometries, angled ridges, abrupt terminations and surfaces that suggested joint articulation. The body was roughly ellipsoidal but broken by lines that aligned too precisely to be natural fault lines. Shadow mapping confirmed that several ridges ran in parallel, separated by equidistant grooves. More unnerving was the presence of symmetry on opposite hemispheres. Twin structures mirrored one another with less than 3% deviation in dimension. This was not the randomness of fractured geology. This was order. The data confirmed a surface devoid of typical cometary features. No crater fields, no chaotic ejecta blankets, no sign of erosion from millennia of solar radiation. Instead, the skin of Atlast appeared unweathered metallic in some spectrums, matte in others. It absorbed infrared in waves, suggesting layered materials with varying thermal capacities. In certain rotational angles, narrow channels could be seen linear troughs that spanned hundreds of meters without deviation. One structure drew particular attention, a flat protrusion nearly 90 meters long, extending from the main body at a precise 14.7 degree offset. The odds of such an alignment forming through chance tectonic displacement in the vacuum of interstellar space approached statistical impossibility. Computer simulations based on natural fracture propagation failed to recreate any analogue. The conclusion was inescapable, if not definitive. Either Atlast was forged through processes utterly unknown to current physics, or it was shaped, deliberately. The community hesitated, unwilling to frame the discovery in such absolute terms, but the silence on official channels stood in contrast to the whispers behind closed sessions. The object behaved less like a comet and more like a shell and architecture waiting to be understood. ThreeI Atlast was no longer just a question of orbit. It had become a mirror, one that stared back with lines too clean, too aligned, too coldly elegant to ignore. The release of the enhanced datasets forced a quiet reckoning. ThreeI Atlast, once tentatively classified as a loosely bound interstellar fragment, no longer fit any familiar category. As new cross-spectral overlays arrived from JWST and ground-based radar, the scientific teams comparing the October and November datasets reached an unavoidable inflection point. The object's features were not simply unusual, they were incompatible with every natural formation model currently used in planetary science. Atlast's surface displayed geometric stability across multiple observational passes, maintaining sharp edges and repeatable shadow fall-off patterns. No natural body, especially one subjected to the chaotic stresses of interstellar travel, preserved such clean boundaries. More troubling were the substrate variations regions that absorbed thermal signatures entirely sat adjacent to sectors reflecting sharply at specific wavelengths. This implied heterogeneous material engineering, not random accretion. Atlast behaved less like a celestial leftover and more like a composite assembly. Rotational analysis introduced further inconsistency. The torque profile calculated from its spin should have fluctuated due to solar wind drag, yet Atlast maintained an almost disciplined rotational cadence. When fluctuations did occur, they happened in discrete steps, abrupt micro-adjustments suggestive of internal regulation. The physics did not match sublimation mass shedding or natural torque damping. Something inside Atlast seemed to anticipate the forces acting upon it. These contradictions accumulated until they formed a single coherent pressure on the scientific narrative. The established models, Cumtree evolution, fractured planetoids, tidal remnants collapsed one by one under the weight of the new evidence. What remained was an uncomfortable proposition, perhaps three. Atlast was not shaped by nature at all. Perhaps the object had undergone processes guided by structure constraint and intent. This conclusion was never spoken aloud in official reports, yet its presence lingered in every private briefing. Researchers who once spoke confidently about natural explanations now paused before offering opinions. Atlast's data had shifted from anomaly to indictment, forcing the scientific community to reconsider not how the object moved, but what it truly was. 3. Atlast no longer resembled a wanderer shaped by chance. It resembled a construct awaiting recognition. The turning point came in silence, not through visual shock, but through cold comparative telemetry. After crossing perihelion, its closest pass around the Sun 3, Atlast began to expand. Radar readings from the Mars Express Array, corroborated by independent interferometry from Earth-based stations, showed a measurable increase in the object's volumetric profile. The change was not ambiguous. Atlast had grown by approximately 14.2% in effective surface area. There were no violent outbursts, no massive jets of gas that could explain a shedding or fracturing of surface layers. Instead, the expansion appeared controlled uniform along the object's longitudinal axis, with no corresponding loss in reflectivity or structural coherence. In other words, Atlast didn't break apart. It unfolded. Standard comet models could not account for this. No known outgassing mechanism, thermal fracture pattern, or volatile base swelling could generate a stable symmetrical increase in shape at this magnitude, especially not post-perihelion, when most comets begin to dissipate. Yet Atlast maintained density integrity, spectral consistency, and reflected mass across all observations. This was not an explosive event. It was architectural. Infrared readings taken before and after the expansion revealed deeper layers of the object with previously concealed absorption bands. These new spectroscopic features matched no known elemental composition typical of icy or rocky bodies. Instead, they suggested heat sink mechanisms, high-capacity thermal chambers hidden beneath the surface now exposed through movement rather than destruction. Simulations attempting to replicate this behavior using natural materials failed under every model. Even objects made of flexible lattice structures like carbon aerogels or polymer chains could not survive the radiation pressure and thermal variation near perihelion without disintegrating. Atlast, however, remained intact, and more than intact, it appeared to adjust. The expansion event also altered the object's light curve in puzzling ways. Rotational phase shifts suggested rebalancing, as though the mass redistribution was intentional, strategically repositioning itself to maintain stability. It did not tumble, it recalibrated. Observers began referring to the event not as a flare or bloom, but as a deployment. The language shift was subtle yet profound. Something that deploys is not acted upon, it acts. Atlast had not endured a random reaction to solar energy. It had responded. By late November, the debate had shifted from physical mechanisms to intentional ones. If Atlast had grown in size, reshaped itself after perihelion, and maintained functional equilibrium, then perhaps it was not passive matter at all. Perhaps it was built to survive solar extremes, or worse, perhaps it needed them. ThreeI Atlast no longer fit inside the vocabulary of comets or asteroids. Its behaviour belonged to a different lexicon, one that had no place in natural astronomy. Not yet. In early spectral surveys, ThreeI Atlast's surface appeared deceptively dim, cloaked in dust and low albedo residue. But as it passed perihelion and reoriented itself following the measured expansion, detailed in prior telemetry, the object began to reveal a contrasting property light. Across multiple observational bands, Atlast exhibited a dramatic spike in reflectivity. This wasn't the chaotic glint of exposed ice crystals or metal inclusions sometimes seen in asteroid collisions. It was coherent, concentrated, and uniform. Light bounced off specific regions with intensity comparable to engineered surfaces, mirroring in some angles the specular return of polished alloys or heat-dispersive composites. Surface spectroscopy from both JWST and ground-based interferometers failed to match the observed spectral signatures with any catalogued mineral or known composite from natural celestial bodies. No basaltic carbonaceous or silicate configuration fit the reflection curve, especially under infrared scrutiny. Instead, these regions exhibited consistent thermal saturation plateaus, suggesting an unusually high thermal emissivity, combined with engineered cooling behaviour. In short, the surfaces didn't just reflect, they regulated. The surface patterns also defied chaotic natural distribution. Shiny, high reflective bands were not randomly placed but aligned in repeating geometric arrays. Some ran parallel along the object's leading edge, while others clustered in hexagonal tessellations spatially consistent across multiple observation angles. This implied underlying intention, not accident. The implications were deeply unsettling. These materials did not merely survive the solar encounter, they appeared optimized for it. Further anomalies arose when examining how the object shed accumulated heat. Rather than radiating thermal energy evenly, Atlast displayed pulse-like emissions, short, intense discharges of infrared radiation at fixed intervals, as if venting or resetting internal systems. No known comet or asteroid has ever displayed such behaviour. And yet Atlast maintained this rhythm undisturbed by solar wind fluctuations. By mid-analysis, planetary materials specialists could no longer entertain conventional models. The consensus, though, never stated officially, was clear: if these surfaces were not natural, they were manufactured. And if manufactured, they belonged to a system, not just a rock. ThreeI Atlast had become more than a comet of interest. It had become a surface one with structure, function, and perhaps even purpose. As higher resolution imaging stabilized post-perihelion 3, Atlast presented a new layer of discomforting complexity. What began as faint notches in low-light profiles evolved into fully visible symmetrical openings, circular, evenly spaced and distributed with almost architectural intent. These were not craters, fractures or gas vents. They were precise. Multiple instruments confirmed their existence independently. Mars Express radar, the JWST near-infrared array, and Earth-based arrays all aligned Atlas bore at least 14 distinct round apertures across its primary surface axis. Each exhibited remarkable geometric uniformity, with diameters clustering around 42 meters and depth signatures tapering with engineered regularity. Their spacing echoed a lattice, not chaos. Statistical simulations were run to quantify the odds of such symmetry, emerging from impact events, thermal cracking, or outgassing instabilities. The result was unequivocal. The probability of randomly forming 14 symmetrically spaced, uniformly sized openings on a single irregular body was calculated at under 0.001%. Even this number, according to analysts, was generous. It did not account for the concentric micropatterns around each aperture or the absence of any surrounding ejector fields. Surface temperature data added another variable. These circular zones emitted cooler than average readings, implying either internal shading or the presence of materials not exposed to direct sunlight. When subjected to solar exposure, they did not demonstrate the heat-up curves expected of natural concavities. Instead, thermal buildup plateaued prematurely, as if self-regulating mechanisms were involved. Morphologically, the apertures appeared beveled at the edge with subtle ridges that acted like stabilizers or reinforcement lines. Such features are unheard of in spontaneous planetary formation. They suggest constraint intent and stress distribution terms belonging more to aerospace design than to astrophysical erosion. The implications did not go unnoticed. In closed-door sessions, some engineers began referring to the apertures as ports, or intakes, quietly shifting their language from passive observation to structural interpretation. ThreeI Atlast was no longer interpreted as simply strange. It was being quietly treated as an object of possible design. And with every new pass, every frame rendered by light years of relay and analysis, the uncomfortable question grew louder. Were these circular openings part of a natural relic, or doors on the hull of something built? As the radar waveforms from the Mars Express deep penetration sequence were processed, a startling internal signature began to form. Buried beneath Atlast's outer crust, a lattice of angular voids emerged, distinct, measurable, and undeniably geometric. Unlike irregular fractures or caverns common to celestial erosion, these cavities formed cleanly defined perpendicular corridors. They intersected at 90-degree angles. The cross-sections, reconstructed from radar pulse returns, showed consistent dimensions. Each tunnel spanned roughly 28 meters in width and maintained height uniformity across several kilometers. This was not a random collapse nor a network of porous lava tubes. There was no evidence of thermal spallation, no branching veins, no erratic curvature. Instead, the paths extended in straight lines, turned sharply, and maintained coherent spacing from one another as if planned. Natural models failed to replicate such organization. No known geophysical process, even under extreme gravitational flux or rotational torsion, could yield such orthogonality over this spatial scale. When superimposed onto Atlast's surface, features the grid aligned loosely with external reflective patterns, suggesting a connection between internal voids and external structural segments. Some passages terminated at what appeared to be chamber-like volumes. Their walls displayed non-random radar reflectivity, abrupt drops and sudden intensifications, implying material changes internal facetting or compartmentalization. The transition zones between tunnel and chamber read more like load-bearing joints than crumbling stone. Analysts attempted to explain the findings through analogues lava tubes on the Moon, fractured strata on Mars, or hollowed-out ice regions within comets. But none accounted for the sheer consistency, symmetry, and straightness of the voids inside ThreeI Atlast. The only comparable architecture, angular grid-like and orthogonally intersecting, came from terrestrial design blueprints. This was not randomness hiding in stone. It was geometry under compression engineering buried in orbit, and it raised a new layer of questions, not about the surface but the thing beneath it. What kind of object carries internal corridors that obey no natural law? Atlast was no longer merely a body with strange material. It now revealed the possibility of interior structure of purpose built into silence. In the weeks following Atlast's perihelion phase, long exposure frames and Doppler tracking from multiple observatories began to converge on a disturbing mechanical pattern. ThreeI Atlast, once assumed to rotate as a single rigid mass, was now exhibiting rotational decoupling. Sections of the object were spinning at varying angular velocities, with clearly defined boundaries between rotating segments. The phenomenon first appeared in photometric fluctuations, subtle light dips and phase offsets that didn't align with a monolithic spin signature. As more frames were collected across different viewing geometries, analysts identified at least 3 major surface panels, each turning along its own rotational axis. One elongated lobe oscillated with a 14.7-hour period, while an adjoining segment lagged behind by 0.3 degrees per cycle. These offsets persisted even after factoring out gravitational influences and thermal inertia. Such behaviour could not be reconciled with conventional comet dynamics. Natural bodies, whether fragmented or loosely bound, tend to exhibit chaotic tumbling or uniform precession. They do not segment into independently rotating shells, and yet Atlas maintained this behaviour consistently without signs of disintegration or momentum loss. Infrared imaging added weight to the anomaly. Temperature distribution maps showed distinct frictional heating at the seams, between moving segments suggesting contact surfaces or rotational resistance. These thermal deltas were not random. They clustered along curved junctions resembling bearing rings, structures designed to reduce torque and enable controlled spin. Several simulation models were run to test if such decoupling could emerge from collisions or differential mass ejection. None reproduced the observed motion without catastrophic failure. The only scenario that matched the data was mechanical, that Atlast housed nested components connected via rotational bearings or interlocking hubs. While no direct images captured internal mechanisms, the implication was loud enough. Atlast might not be a relic of nature, it could be a composite body with engineered articulation. The idea of spin-bearing joints in an interstellar object was no longer absurd. It had become a plausible answer to a question no one had dared to ask. What kind of intelligence allows an object to orbit with its own internal choreography? As 3, Atlast receded from perihelion. The James Webb Space Telescope locked its infrared spectrometer onto the retreating object and captured an unexpected constancy, a surface-wide temperature of approximately 280 Kelvin. That figure, roughly 7 degrees, remained remarkably stable across days, with only minor variances defying expectations for a body cooling after solar proximity. No comet or asteroid had ever exhibited thermal behaviour this uniform post-heating. But beyond the general equilibrium, a deeper irregularity emerged. Layered atop this flat thermal field were 47 distinct hot points scattered asymmetrically across the surface. Each exhibited periodic temperature fluctuations rising and falling in precise clock-like cycles. The intervals between pulses were not chaotic or solar-driven. They followed a coherent pattern with synchronized peaks recurring every 247 seconds. These were not residual ventings or fading outgassing events. No dust plumes or ejection jets were associated with the hot nodes. Moreover, the heat pulses did not spread or migrate, they remained geographically locked, as if anchored to fixed emitter ports. Spectral analysis showed no corresponding chemical activity that could explain sudden thermal surges. Instead of behaving like a body passively shedding solar energy, Atlas seemed to be maintaining internal regulation. Each pulse resembled a controlled emission, like the rhythmic discharge of onboard systems. When mapped together, the 47 hotspots formed partial arcs and incomplete lines resembling nodes in a grid. And when their timing patterns were modelled collectively, they exhibited beat frequencies suggesting coordination, not isolation. Astrophysicists attempted to match the pulses to known thermal resonance phenomena, but no natural process offered a stable 280 K backdrop paired with 247 second interval fluctuations across fixed spatial anchors. Even the idea of latent chemical reactions or rotational friction failed under scrutiny. No volatile known to science behaved this way. At last it now seemed possessed an internal thermal consistency and modular heat signatures that more closely resembled a managed energy system than a passive celestial rock. It pulsed not in chaos but in rhythm, and rhythm in the language of physics often implies intent. Among the most puzzling signatures observed from ThreeI Atlast was the continuous emission of molecular oxygen O2 along its outbound trajectory. Initial detections from UV spectroscopy were dismissed as background contamination, but repeat passes from the Hubble Space Telescope and ESA's solar orbiter confirmed the same spectral lines with increasing clarity. Atlast was shedding pure molecular oxygen into space at a steady rate. What made this so striking was not merely the presence of O2, but the persistence. Comets are known to carry embedded volatiles, including water ice carbon dioxide and, in rare cases, traces of oxygen. But such emissions are typically short-lived fading as the volatile layer depletes. Atlas defied that pattern. Its oxygen signal remained constant for over 29 days, with no visible diminishment even as other volatiles dropped off. This raised a new problem: replenishment. For molecular oxygen to remain in detectable quantities over such duration, it would either have to be stored in vast layered reservoirs or regenerated in real time. Yet Atlast's surface composition did not suggest any ice-rich strata or buried peroxides that could explain prolonged oxygen release. And chemical pathways for producing O2 in vacuum under solar radiation are rare and inefficient. The anomaly deepened when researchers noted that oxygen emissions spiked in phase, with the thermal pulses from the 47 hotspots observed earlier. Each wave of oxygen coincided within seconds with a synchronized temperature rise. No known natural comet exhibits such correlation between thermal modulation and gas release, let alone for a single purified molecule. This behavioral loop pointed to something intentional. On Earth, only two systems are known to produce molecular oxygen, cyclically: biological respiration and engineered electrolysis. Both require compartmentalization, energy flow, and feedback control. Was Atlast exhibiting something akin to a self-sustaining loop, a closed system where oxygen was generated, stored, and released in a coordinated cycle? If so, it wouldn't just challenge comet models. It would redefine our concept of what can persist in interstellar space. Not a rock, not a ruin, but possibly a living system or a machine that breathes. Roughly 2 weeks after perihelion, new silhouettes began to appear on the surface of ThreeI Atlast. Images returned from the Mars Express radar pass and deep field alignments from the James Webb Space Telescope revealed vertical protrusions columns that had not been present in any prior scan. Rising between 30 and 60 meters above the surface, these structures were symmetrical, steep-walled, and cast long, crisp shadows against the reflective terrain. The timing was inexplicable. Prior to perihelion, Atlast's profile was mostly irregular but natural fractures, pockmarks and crustal ridges. But in the post-perihelion window, something changed. These upright features appeared fully formed with no evidence of progressive outgassing fragmentation or slow build-up that would typify cometary jets or pressure-driven bulges. What stood out even more was their alignment. The towers were not scattered randomly. They appeared in radial clusters, some forming concentric rings, others spaced at near equal distances as if mapped by a grid. Radar shadows confirmed consistent elevation across several columns within centimeters. No known natural geological process could produce such precision on a rapidly rotating, unstable object. The prevailing hypothesis among conventional theorists suggested cryovolcanic spires or transient ice pillars formed through phase change dynamics. But this theory collapsed under thermal data which showed no sufficient temperature gradient to support such ice extrusion. Moreover, the base of each tower exhibited unusually high reflectivity, consistent with metallic or ceramic composites, not volatile ices or carbonaceous dust. These characteristics led to a disturbing question. Were these not natural formations at all, but engineered constructs? The term artificial crept into internal memos, followed by cautious speculation that these were support pylons, antennae, or energy dispersal arrays. ThreeI Atlast now appeared to be more than anomalous. With upright structures manifesting post-perihelion, it crossed a threshold. This was no longer just a comet behaving strangely. It was increasingly a system, one that might be adjusting, adapting, or revealing itself in stages. By the time ThreeI Atlast completed its perihelion passage, a disturbing pattern had emerged. Across thousands of data points spanning radar, infrared, and spectroscopic signatures, the object defied the natural expectations of any known comet or interstellar rock. 5 distinct anomalies stood out not in isolation but in coherence. Together they formed the pillars of a hypothesis that no longer seemed fringe at last might be artificial. First, geometric precision radar mappings from ESA's Mars Express, and data processed through JWST revealed symmetrical depressions and structural voids embedded within Atlast's body. These were not scattered randomly as would be expected from impact scars or sublimation pits. Instead, they followed radial alignments, equidistant spacing and polygonal borders, some octagonal, others square. At resolutions reaching 12 meters per pixel, the shapes held up exhibiting internal consistency, down to margins of less than 1.4%. No stochastic natural process, thermal cracking, micrometeorite bombardment, or gas venting could yield such architectural order. Second, thermodynamic stability. Whereas natural comets undergo volatile swings in temperature near perihelion, ThreeI Atlast held a near-constant thermal envelope of 280 Kelvin. This thermal behavior was punctuated by 47 discrete hotspots across its surface. What was anomalous wasn't their intensity but their rhythm. They pulsed in near-identical cycles distributed evenly over the object's rotation. Each pulse rose and fell in lockstep as if regulated by an internal clock. Passive materials do not do this, not without feedback systems, not without design. Third, post-perihelion growth. Following solar perihelion, Atlast increased in effective cross-sectional area by 14%. This was not caused by fragment dispersion or ice bloom, as no mass ejection was detected. Instead, the object's surface seemed to expand, certain segments unfurling like petals, while others extruded vertical formations. Radar shadow measurements confirmed that these growths were cohesive and maintained angular momentum, meaning they remained attached, not expelled debris. Comets erode. They do not grow. Fourth, atmospheric composition. Spectroscopic readings from multiple observatories, including ground-based LBT and the JWST, consistently detected molecular oxygen, O2, streaming from multiple vents. This was puzzling on two fronts. First, oxygen is highly reactive and should not exist freely unless constantly replenished. Second, the volume and steadiness of the O2 emissions implied regulation. Some hypothesized a subsurface biosphere or cryogenic recycling loops, both of which require compartmentalized structure and energy flow, both of which exceed what a cold rock should be capable of. Fifth, structural complexity. The deepest radar penetrations, particularly from the coordinated MRO-JWST sweeps, uncovered intersecting corridors within Atlast, with angles at precise 90-degree intervals. The corridors were not deep but layered, suggesting floors, ceilings and junctions. Beneath one such layer, a large hexagonal cavity was mapped spanning over 400 meters across, with consistent wall reflectivity akin to ceramic alloys. Random caverns unlikely. Caves do not come with parallel walls and right-angled turns, especially not in vacuum-sculpted space rock. Individually, each of these anomalies might be debated, even dismissed. But collectively, they converged. 5 domains: geometry, thermal regulation, volumetric expansion, chemical recycling, and internal structure. Each pointed not just to deviation, but to intention. 3i Atlast wasn't merely strange. It was behaving like a system, modular, self-regulating, and possibly intelligent. The astronomical community stood divided, but among those paying attention, a new phrase began to echo through classified briefings and closed-door symposia. This isn't a comet anymore. Despite the wave of excitement rippling through scientific circles, a substantial faction of astronomers and physicists refused to embrace the artificiality hypothesis surrounding 3i Atlast. To them, the 5 so-called pillars of artificiality were not pillars at all, but shadows cast by incomplete data and cognitive bias. Their argument was not rooted in hostility to new ideas, but in a deep caution born from decades of chasing false positives. At the heart of the skeptical response was the assertion of insufficient comparative baselines. 3i Atlast was by definition only the 3rd recorded interstellar object in human observation, after Oumuamua and 2i Borisov. None of these objects had been observed with the kind of resolution, spectral layering, or multi-platform triangulation that Atlast received. Without a statistically significant sample size, skeptics argued how could anyone distinguish between the truly anomalous and the simply unfamiliar. Perhaps other interstellar bodies exhibited similar behaviours, but passed unnoticed due to observational limits. Equally emphasised was the problem of interpretive overreach. In the skeptical view, the high-resolution radar images showing geometric cavities, perpendicular corridors and pulsing heat zones were not necessarily indicators of design. Rather, they could be artifacts of pareidolia, the human brain's tendency to find patterns where none exist. Given the sheer volume of data gathered by MRO-JWST and Mars Express, it was statistically inevitable that some segments would resemble artificial structure purely by chance. Then came the question of confirmation bias. Skeptics pointed out that once the artificiality hypothesis gained public traction, amplified by media forums and a few high-profile theorists, researchers began looking for patterns rather than neutrally cataloguing them. Analysis drifted from documentation to interpretation, from inquiry to implication. They questioned whether those supporting the artificial origin theory were selectively emphasizing data points that supported their conclusions while minimizing or ignoring those that did not. An additional critique focused on semantic drift, the subtle but impactful way language shaped perception. Terms like corridors, hubs, or growth segments carried architectural or biological connotations that primed observers to interpret raw data through a lens of design. One planetary geologist noted that in any field, the moment descriptors shift from neutral void elevated region to suggestive tower atrium, objectivity begins to erode. Furthermore, skeptics argued that post-perihelion changes, including the apparent 14% increase in volume, could result from non-uniform outgassing, a behaviour not unprecedented among volatile-rich bodies. The lack of visible mass ejection might be explained by directional venting into shadowed regions, or outflow composed of a large-grain low-albedo material, essentially invisible at the wavelengths used. The emergence of molecular oxygen also sparked scrutiny. While O2 production had once been considered an unambiguous marker of biology or technology, newer models allowed for sustained oxygen release via surface peroxide interactions under extreme thermal cycles, especially in interstellar ices processed by cosmic rays. For these critics, caution was not cowardice, it was rigour. The history of astronomy, they reminded the community, was littered with sensational claims that dissolved under peer review. They did not deny Atlast's strangeness. They challenged the interpretation of that strangeness as proof of intent. In their view, the object remained a mystery, but one that demanded more data, not premature conclusions. Yet even amid their caution, an uneasy truth lingered. ThreeI Atlast had forced even its doubters to look twice. And in science, that alone is not a dismissal, it is disturbance. Caught between escalating enthusiasm and rigorous skepticism, a third voice emerged, measured, deliberate and conscious of the stakes. These were the scientists who neither dismissed the anomalies of ThreeI Atlast, nor rushed to proclaim artificiality. They stood at the tense intersection of wonder and restraint, advocating for a posture rooted in data, not narrative. To these researchers, the case of Atlast was unprecedented in its complexity. It had defied expectations on multiple fronts, from its geometric features, an unexplained volumetric increase to the stable thermal zones and persistent molecular oxygen. Yet while each detail suggested something more than natural coincidence, none could independently confirm non-natural origin. It was the pattern, not the parts, that raised eyebrows, but patterns they warned could emerge from chaos. They urged the community to resist the seductive gravity of conclusions. Instead of asking, "What is at last?" they reframed the question, "What range of explanations remain viable given current data?" Some leaned toward exotic natural processes still outside our catalogued experience. Others admitted privately that if Atlast was indeed artificial, the implications would redefine not only astronomy, but the position of Earth in the cosmic timeline. Still, they cautioned against emotional drift. Curiosity was a virtue, they reminded their peers, but so was discipline. Jumping to conclusions, however enticing, could corrode credibility and distract from what mattered most, continuing to observe, to model, to test. And so the centrist stance held firm. ThreeI Atlast had not yet revealed its nature. The truth might be out there or hidden in plain data. Either way, it demanded not belief, but vigilance. Even if ThreeI Atlast bore no sign of aggression, no trace of hostility, its very presence posed a dilemma humanity was not prepared to solve. For the first time, scientists and policymakers were forced to consider a chilling scenario. What if the object wasn't a threat, but a mirror? Not a weapon, but a witness sent from elsewhere by something far ahead of us. From its unexplained geometric alignment to the thermal regulation zones that maintained precise 280K stability, ThreeI Atlast consistently demonstrated features that, if artificial, suggested an engineering capacity centuries, perhaps millennia ahead of ours. The symmetrical boreholes, the independent rotating segments, the surface reflectivity beyond any known comet. Each anomaly, when taken in isolation, had room for debate, but together they hinted at something deeply uncomfortable design without intention of contact. And that's where the real danger began, not from what Atlast might do, but from what it already implied. If it was a vessel, a probe, or an autonomous construct of extraterrestrial origin, then we were not alone, not anymore. And worse, we weren't even first. In military and intelligence communities, discussions quickly evolved from curiosity to contingency. A non-hostile system can still destabilize human systems just by being seen. Technological inferiority has always bred panic, whether in historical conflicts on Earth or projected out into space. Atlast did not need weapons to challenge us. Its very existence could fracture geopolitical trust, which governments knew what and when, which agencies had kept secrets, and which had been blindsided. The object's overflight path, its silence, its radiant spikes of oxygen, All could be interpreted, twisted, politicized. Diplomatic circles began drafting protocols for contact that might never come. Others worried less about communication than exposure. What if Atlast had been observing us for decades? What if it had been transmitting our broadcasts, our movements, our conflicts back to something larger? More disturbingly, what if we'd been tested? Strategists drew analogies to Earth's own behaviour, how we studied ants not out of malice but indifference. 3. Atlas might not be here to destroy us. But if it was the product of a civilization orders of magnitude more advanced, then we were not actors in this encounter, we were subjects. And in that asymmetry lies the ultimate risk. Not invasion, but irrelevance. With mounting evidence pointing toward artificial origin, the international science and defence communities converged on a single consensus. Inaction was no longer a neutral stance. Whether ThreeI Atlast was a passive structure, an automated probe, or something entirely beyond classification, its repeated anomalies, thermal regularity, geometric features, independent mechanical segments demanded a formal response framework. And from the resulting strategy matrices, 3 distinct approaches emerged. Option 1, launch an intercept mission. This was the boldest and riskiest strategy to send a spacecraft on a trajectory to directly rendezvous with Atlast. Advocates argued that only physical proximity could resolve the object's ambiguity. Spectral data and radar imaging, while valuable, left open too many interpretive gaps. Was its surface truly metallic or just coated in reflective dust? Were the interior structures static, or did they respond to solar radiation dynamically? A mission akin to the Rosetta lander or the OSIRIS-REx sample return model might offer decisive insight. However, critics warned that even a non-invasive approach could trigger unknown defense mechanisms if the object possessed any. Moreover, the timeline was tight. Atlast's trajectory would soon carry it beyond reachable range without deep space propulsion. To launch now meant cutting through regulatory red tape, cross-agency coordination, and political friction faster than any mission in recent memory. Option 2. Continue remote observation and attempt signal-based communication. A more conservative camp advocated caution over contact. Let Atlas pass through the solar system. Let it show its behaviour under varying stellar conditions. If it responded through shifts in rotation emissions or directed radiation, it would confirm its interactive capacity. Meanwhile, Earth could attempt non-invasive communication laser pulses, directed RF packets, pattern transmissions using prime numbers, or universal physical constants. SETI institutes and space agencies drafted proposals for signal experiments encoded with mathematical simplicity and non-aggressive intent. But here too lay risk. To signal was to announce ourselves, and if Atlast had not yet revealed awareness, the very act of calling out might awaken it or whomever might be listening. Option 3. Prepare planetary defense protocols. Though the least discussed in public contingency plans were already in motion behind classified doors. What if Atlast altered course? What if it deployed satellites, probes, or worst case entered a descent trajectory toward Earth? No evidence supported such hostility, yet defense agencies could not ignore the probability tree. Neutrality is not safety. And in the absence of understanding, any shift in the object's behaviour could cascade into panic. Defense strategists updated response thresholds. Automated warning systems were recalibrated to include non-ballistic, non-terrestrial inbound anomalies. Simulation environments were loaded with new datasets to model Atlast-like intrusion scenarios, and satellite constellations quietly adjusted their observational tasking. Across these 3 approaches, engage, observe, defend ran a single thread. No one knew what Atlast was, but the margin for error was shrinking. The paradox of a non-hostile anomaly is this: it leaves humans to confront their own projection. Some saw Atlast as a gift, others a test, still others a threat wrapped in silence. Each reaction said less about the object and more about us. But no matter the interpretation, one truth had crystallized. From here on, Earth had to act like it was being watched, because perhaps it was. Faced with an object that challenged physics logic and precedent, the global community slowly began to accept a daunting reality: no single strategy would be sufficient. ThreeI Atlast was too large, too silent, and too anomalous to be resolved by a binary approach. Any rigid commitment, whether aggressive pursuit or passive observation, risked putting humanity into a corner it could not escape from. Thus emerged a 4th model, the multi-vector protocol, a dynamic layered approach to avoid strategic blindness. This integrated solution didn't prioritize one path, but instead framed 3 concurrent operational layers, each adaptable to new data, each capable of independent acceleration if Atlast changed behavior. Layer 1 coordinated remote surveillance. The most immediate and least invasive step remained high-resolution observation. Space telescopes like JWST and Earth-based interferometers were tasked with synchronized monitoring windows. Dozens of narrow-band frequency bands were allocated for passive listening. Every slight alteration in Atlast's trajectory, thermal pattern, or emissions profile was logged in real time. Machine learning models were deployed to compare its motion signature with known natural bodies, rechecking for irregularities previously missed. This layer acted as a stabilizer, keeping humanity informed and any sudden changes instantly flagged. Layer 2 contingent contact preparation. While direct communication remained controversial, preparation was non-negotiable. A dedicated sub-network of agencies including NASA, ESA, CNSA, and non-governmental SETI collaborators began constructing communication protocols built around universal constants and non-threatening markers. These included spectral light pulses encoded with Fibonacci sequences, gravitational harmonics, and isotopic signal tests. At the same time, policy work accelerated. Who would speak for Earth? What content was authorized to be sent? Could AI-generated language remove anthropocentric bias from communication attempts? The goal was not to rush contact, but to ensure that if contact occurred, humanity would not respond with confusion and contradiction. Layer 3 Dynamic Defense Readiness. In parallel with diplomacy and science, military and civil defense infrastructure were quietly recalibrated. This layer did not assume aggression from Atlast, it anticipated fallout from human reaction. Any misinterpreted movement, sudden burst of energy, or unexpected rotation of Atlast could trigger geopolitical panic. Thus, response systems were linked across spacefaring nations to prevent unilateral escalation. Early warning protocols now included non-terrestrial unknown trajectory flags, and AI analysts were inserted into global decision loops to ensure interpretive lag didn't lead to catastrophe. Together, these 3 layers formed an adaptive non-binary framework. Their brilliance wasn't in assuming the nature of Atlast, but in refusing to assume at all. Instead of leaning into certainty, the protocol accepted uncertainty as the operative field. Flexibility became a virtue. Every model was probabilistic. Every plan had branches. Crucially, this integrated model avoided the most dangerous condition of all strategic paralysis. By acting on multiple fronts simultaneously, Earth bought itself something it hadn't had since Atlast was first detected time. And perhaps, just perhaps, the presence of ThreeI Atlast was not just a mystery. It was a rehearsal for something larger, for the possibility that the cosmos had never been empty, only waiting, and now, watching. 3. Atlast now recedes into deep space, passing behind the solar glare like a question swallowed by fire. Its final signal, if it was ever sending one, remains unread, and in its absence, Earth is left not with answers, but with a mirror to our readiness, our fear, our capacity to think beyond what we know. Was it a probe, a structure, a relic, or simply the most misunderstood comet in recorded history? Whatever Atlast was, it has altered the scientific trajectory of our time. We now calibrate our sensors not only to detect motion but intention. We do not simply watch the sky for what moves, but for what thinks. Perhaps Atlast was only a shadow of something greater. Perhaps it was the first note in a language we have yet to learn. But one thing is certain, the silence it left behind is not empty. It is charged, with probability, with responsibility, and with the quiet, heavy knowledge that we are not prepared, not yet. But maybe now we begin.